Okay, here's a brief overview of gases. We're going to describe them, take a look at air, we'll study them without messing with them, we'll go ahead and squeeze them or heat them, check out the effects, and we'll consider what really happens out in the real world. So let's describe them. Let's begin by considering air. Air is mostly nitrogen, and the rest of it is oxygen. There are some minor components as well, including carbon dioxide and some other gases. Fine, that's air, a clear, colorless, invisible gas. Let's consider the elements, and of the 118 or so known elements, it's surprising how few of them exist as gases in their native, state, 1 atmosphere, room temperature. Most of them are metals. Of course, most gases are not elements. Most gases are in a molecular form. How about altitude effects? What happens as you go up? Well, as you go up, the pressure decreases, the concentration of the molecules decreases, and so the pressure decreases. You have to hit about 4 miles or 20,000 feet above planet Earth before you get down to about a half an atmosphere, and that's low. Go even higher than that, up to, say, 10 miles, and you certainly would need some sort of breathing apparatus because the pressure is only 0.2 atmospheres. Okay, let's take a look at them just physically. Suppose we're curious about pressure or volume or the number of moles or the temperature or its molecular weight or its density. For that, usually people use the ideal gas law, but occasionally there's a more convenient law depending on what you want to get, which I call the density law. If you happen to be at 0 degrees Celsius and 1 atmosphere, congratulations, you are at standard temperature and pressure, and there's a special number for there. If you have a mole of any gas or mixture of gases, you'll have 22.4 liters of volume. Very handy number to know. If you want to study a mixture of gases, all of these formulas still apply because the identity of the gas doesn't matter. They're essentially little points that bounce around within a space. And so that's it. Now, if it is a mixture and you're curious about the pressure, it's just the number of dots, if you will. The number of molecules is proportional to the pressure. So that means number of molecules, that's your mole fraction. And for that, we have that formula there. If you want to consider how fast they're moving relative to one another, the take-home message is that the lightweight gases will move faster by their square root. In other words, twice as light does not mean twice as fast. It means 1.414 times as fast. And for that, we have Graham's law. Okay, let's mess with them. Let's squeeze them. Let's heat them. Let's compress them. If we can, consider the effects. Two systems. One is expandable and compressible. The other one has a fixed volume. You see them both all the time. If we heat this one, it can expand, and so that's what will happen. This is Charles's law. As the temperature goes up, the volume goes up, or vice versa. This one cannot expand, so it will pressurize. This is the dangerous law, Gay-Lussac's law. It will pressurize, and at some point it might burst. If you cool it, the opposite happens. This one will contract. That one will depressurize, simply meaning that the pressure will get lower. This little number will go down. If you compress it, you can for this one. And for that one, that is going to pressurize it, right? It'll just push down and pressurize that system. This one, you can't compress it, so it doesn't apply. If you expand it and pull this valve back or somehow open up a balloon to make it bigger, that doesn't mean adding more molecules, by the way. These are all for n constant systems, right? It's closed up. No molecules can get in or out. But if we can expand it, and for here we just pull up the valve, this thing will depressurize. The pressure will go down. You're creating a vacuum. This one, you can't mess with the volume. So if you consider doing both, it only applies to this one. And for an expandable system, we could push it down and heat it at the same time, for example, and we have a combined formula to figure out the effects there. You would need 5 of these 6 in order to solve it. And it doesn't apply to this system because it is fixed volume. Final question, what really happens out in the world? Consider this demonstration device where you can change the volume and investigate how that affects both the temperature and the pressure. Which one will change? If you ask a lot of people, including teachers, you're going to get different answers. After having studied all this, it's such a simple question. Can we change the temperature of a gas by simply, for example, pressurizing it? What you observe for this system, which can only move very, very slowly, you have to screw this thing down, is you get about a 99% volume change as I should say pressure change. As the volume goes down, the pressure will go up. You will see a couple of degrees change, but when you consider that you're supposed to use Kelvin, you must use Kelvin, it's pretty inconsequential. So you might be led to believe, the temperature really can't be changed with this thing. It's just simply Charles' law. However, consider the fire syringe, where if you smack down on one of these things, it can get so hot you can light fire to a piece of cotton. So the temperature goes up dramatically. This is really the realm of physics where it's a force-dependent situation. Okay, this is a brief overview of gases.